In section 3 we talk about controllability and observability. These are very important concepts. So before the design of a state feedback controller, you should always check controllability, and before the design of a state observer, you should check observability. Well, the concepts of controllability and observability describe the interaction in a system between the external world, that's the inputs and outputs, and what happens inside the internal variables, that is the states. Loosely speaking, that means in words, controllability is the property that indicates if the behavior of a system can be controlled by acting on its inputs. And observability is the property that indicates if the internal behavior of a system can be detected using the outputs. So let's define controllability and observability more formally. Controllability relates inputs and states, so therefore we are not interested in the output equation. This equation is irrelevant, and we are only interested in the state equation, right? And in the state equation we have the matrix A, the state matrix, which is n by n. N is the number of states, and B, well, the control matrix, which is n by m, where m is the number of inputs. So the definition is as follows. We say that the pair AB is controllable if for any initial state x0 and any final state x1 there exists an input that will transfer x0 to x1 in a finite time. Otherwise we say that AB is uncontrollable. So if we choose any initial state x0 and any final state x1, there must exist for each of these cases an input that transfers the input state, the initial state, to the final state in a finite time. For observability, we are interested in the relation between the states and the outputs so that the inputs are irrelevant. So the matrices B and D do not play a role, and so we consider the unforced system that is given over here. As before, A is an n by n matrix and C is a p times n matrix. P is the number of outputs and n is the number of states. So the pair AC is said to be observable if for any unknown initial state x0 there exists a finite time t1 such that the knowledge of the output on the interval 0 t1 is sufficient to determine uniquely the initial state x0. Otherwise the pair AC is said to be unobservable. So the idea is, well, by looking at the output in a sufficiently long time, is it possible to estimate the initial state x0? We can now ask the question why a system would be uncontrollable or unobservable. So why would there be uncontrollable or unobservable modes? Well, a first reason is redundant states. Assume that the system can be described by the following state equation, but that unintentionally we've added more state variables, and that these state variables are proportional to those already present in the state vector. This means that we can define them as follows. Okay, for instance, if x is equal to x1, x2, right, and we add unintentionally a state z, which is x1 plus x2, then in this case the f would be simply 1, 1. Right? So if we take the derivative of this equation, this is what we obtain, and if we add or inject the original state equation, this is what we obtain, right? And now, if we write the state equation that consists of the original state with the states that we've added unintentionally, you would have this description over here. And of course, this state equation is uncontrollable, okay? Because you see here that really in our example the state is x1, x2, z, right? But this is equal to x1, x2, x1 plus x2. So it would be impossible to take the system from the initial state, for instance 1, 1, 2, to the state 1, 1, 3, because this is impossible, right? Because the third state is linked to the first and the second state. I will now show you that it is, well, quite easy to make such a mistake. So assume that we want to obtain a state space description for the system that is given over here, and it's the same system that we have treated before, except here that there are two inductors in parallel, L2A and L2B. So if you remember, what you should do to see how many states you need is to look at the number of independent energy storage elements. And if you do that, you will see, of course, that, well, the energy storage that is in L2A is dependent to the energy storage on L2B, because the voltage that they see is exactly the same, okay? So really, there are only 3 independent energy storage elements, okay? So what you should do is construct a state space description with only 3 states. But the mistake is very easily made, okay? And if you write a state space description with 4 elements, EL1, EL2A, EL2B, and VC, using these equations, this is what you will obtain, okay? And this state space description is not controllable, okay? Because EL2A and EL2B are dependent variables. Such a realization is called not minimal. Well, if you look at the 2 equations over here, you should realize that EL2A and EL2B are indeed dependent variables, and that the relation is as follows. So you can construct a realization using EL1, EL2A for instance, and VC, and then in this relation what you inject in here is this relation over here, okay? So you obtain this equation here, and here you obtain then the realization with 3 states, and this realization is indeed controllable, okay? And it is called minimal. So if you want to design a state space controller, you should use the state space description with only 3 states, because this realization is minimal, it is controllable. Well, secondly, systems can be uncontrollable just by construction. If you look at the 2 systems over here, well, the motion of the masses is coupled because of the forces being applied on M1 and M2 being equal but in opposite directions. So only the distance between the 2 masses can be controlled in this case. It's obvious that it is impossible to control x1 and x2 independently of one another. So a third reason could be that there is too much symmetry in the system, and this is typically the case in an electrical bridge network, because here you would have R1 C1 is equal to R2 C2 for instance. So to see this, let us write a model of the system. So C1 V1 dot, that's the current that flows here, well, comes from this current and this current over here. This current is, well, V minus V1 over R1, and the other current, this one here, is V2 minus V1 over R3. Okay, and the other equation is C2 V2 dot, that's this current, okay, is the sum of those two currents here. This one here is V, the input, minus V2 over R2, plus this current over here, and that's V1 minus V2 over R3. So these are the two equations of the model that we have derived on the previous slide. So here we can remove the C1 and C2 and put it over here. C1, C1, C2, and C2. And if you're now interested in the difference between V1 and V2, we'll call it V bar, you can write the dynamics of V bar as follows by simply taking the difference of these two equations. There will be, of course, a dependence on V1, V2. This is not so important, but we are interested in the link with the input, and you'll have a term plus 1 over R1 C1 V, right? Here it is, minus 1 over R2 C2 V, and here it is. Okay, if you put everything under the same denominator, you see that the dependence of V bar dot on the input is given over here. So if the bridge is balanced, and this is what we mean by too much symmetry, R1 C1 is equal to R2 C2, and this term drops out. Okay, so the voltage V bar cannot be influenced by V, and it will be decaying to 0. This voltage is no longer controllable. So a fourth reason, and here it has to do with observability, a system can become unobservable if a state is not measured and that this state is not fed back to a state that is indeed measured. And here we have such a situation. Okay, and this situation models the case of the system M that is subjected to a force. So the equation of motion is quite easy. Mx double dot is equal to F. So x double dot is equal to F over M. Right? So we have indeed F over M x double dot. We integrate twice and we have x. So we know that the state is x dot and x, and we see that we only measure x dot here. So x is not measured and there is no feedback to a variable that is measured, which is in this case x dot. Okay, so this system will be unobservable. If we make a slight change to this system and we put here a spring, then this system will be observable, as we will see. We have to adapt our equation of motion. We have the force coming from the spring, so we have minus k over m x, and we have to make a change in the model here in the graphical representation of this equation. So we have here k over m So now we have a graphical representation of the equation that is over here. Well, the situation is the same. We still only measure x dot, but now in this case the unmeasured state is fed back well, up front x dot, so it has an influence on x dot, so the system is now observable. We can observe x through x dot, right? So let us now write the state space description of the original system in black and the one in blue, and we'll use that later once we have a test for observability to see that the original system is indeed unobservable and that the new one here in blue is indeed observable. Okay, so remember that the states are x and x dot. So here we'll have x dot and x double dot. This is the A matrix. Here we'll have the B matrix and F, right? And in our case, we're only measuring x dot, so we'll have 0, 1, x dot, right? So the A matrix, well, x dot is equal to x dot, so we have 0, 1, we have a 0 over here, and with the original system we have simply x dot is f over m, so we have 0, 0, 1 over m, right? And with the new system, the 0 here is replaced by minus k over m. Okay, so we have now a state space description of the original system, the one that is not observable, and we have now also a description of the modified system with the spring, and we will see later that this system is indeed observable because the unmeasured state is fed back to a state that is indeed measured, which is x dot. Well, the fifth reason for having systems that are not controllable and or not observable are pole zero cancellations. So assume here that the system takes this form over here. We can compute the associated transfer function, and remember that we need to consider Si minus A inverse, that's A, B here and C, right? So this will be S plus 1, 0, 0, S plus 2 inverse. So this is 1 over S plus 1, S plus 2, and then we need to interchange these two, S plus 1, 0, 0. And if you now compute this quantity over here, 1 over S plus 1, S plus 2, S plus 2, 0, 0, S plus 1, and B1, B2, you'll end up with this transfer function. And as you can see, for instance, if B1 is 0, okay, there is no way that you can influence the first state through the input because B1 is 0, and you cannot influence the first state through the second one because we have a 0 over here. So the system becomes uncontrollable because it is not possible to control the state x1. But if you look at now at the transfer function, you see that if B1 is equal to 0, this term disappears, and what happens is that S plus 1 gets cancelled out of the transfer function. Okay, so if B1 is equal to 0, it becomes uncontrollable, and S plus 1 gets thrown out of the transfer function. You have something similar if C1 is equal to 0. Again, S plus 1 is cancelled out of the transfer function, but now the system becomes unobservable. Look at C1 here. If C1 is 0, well, you can observe x2, but you cannot see what happens with x1, okay? Because C1 is 0, and you cannot observe the influence of x1 on x2 because we have a 0 over here. So when C1 is equal to 0, the system becomes unobservable and s plus 1 gets cancelled out. Well, we have something similar, of course, if b2 is equal to 0 or c2 is equal to 0. Well, very often the system is non-linear and you have to work with a linearized version of the system around some working point. So what this could be is a linearization of the non-linear system around some working point, and we'll do this in the control lab. And what could happen is that in most cases your system is controllable and observable, but that in some working points you lose controllability and or observability. So now that we have defined controllability and observability, it is time for tests to check if your system is controllable and or observable. So the pair AB is said to be controllable if the following matrix, which is called the controllability matrix, is of full row rank. This means that the rank is equal to n. And well, to see what is full row rank and what is the rank of a matrix, well, you should have a look at the course that is associated to this teaching unit. It forms Control 1, and this course is Linear Algebra and Applications, right? But full row rank means that all the rows of this controllability matrix must be independent, okay? Well, note that this controllability matrix is constructed of B, okay? Well, B is n times m. AB is square B up to an minus 1 B, where n is the number of states. Okay, well, the product AB will also be n times m, and this will be the case for all the other products that will follow. So you see here that this matrix lives in n times n m, right? So it has, well, at least this, if m is larger than 1, many more columns than there are rows. If m is equal to 1, so if the system has 1 input, the controllability matrix is a square matrix. Well, as you will see in the course of linear algebra, the easiest way to see if your controllability matrix has full row rank is to use elimination. So when you start to use elimination and you produce a row full of zeros, then you know that your system will not be controllable. The proof of this theorem is given in the course, but it's there only for your information, so I will skip it in this video presentation. So here's the test for observability. We say that the pair AC is observable if the observability matrix has rank n. We will see that this matrix lives in Rnp times n, so it has n columns. So if the matrix has rank n, it must mean that it has full column rank. So here again, have a look on the course on linear algebra. This observability matrix is constructed from C, Ca, and up to the product Ca to the power n minus 1. N is the number of states. C lives in Rp times n, so C has dimension p times n. This one has also, if you multiply C and A, has also dimension p times n, and this is also the case for all other products that will follow. Okay, so indeed we can see that the observability matrix lives in R and P times N. If P is equal to 1, then the observability matrix becomes a square matrix. Okay, so to test if this observability matrix has full column rank, you can use elimination. So again, the proof of this theorem is given in the slides, but I will skip this proof in this video course. We have seen earlier that if a state is not measured and not fed back to a state that is measured, we lose observability. It was the case in this example over here. Notice that x is not measured, right? And it is not fed to the state that is measured, which is x dot. So we had said here we'll lose observability. It's kind of logical. If we integrate x dot, we can obtain x up to a constant, right? So if we test observability using the test, we should see indeed that this system is not observable. Remember that this was the description, the state space description. For observability we need C and A. First row is C and the second row is CA, and here we produce a row of zeros. So this system is not observable, and you can see this using the test, right? So we had seen that if we modify the system by adding a spring, well, the equations of motion are changed. As you can see over here, there's the appearance of a minus k over m, and in this representation of the system you see that now, although x is not measured, well, there is a feedback of x to x dot that is measured. So you can see the influence of x through x dot, and we had said, well, this system will be observable. So we can now use the test for observability and see if this is true. Remember that the observability matrix uses C and A, so the first row is C, is unchanged, and now CA is a vector with minus km0. So if k is different from 0, so we see here that the system is observable, and this is confirmed with our test for observability. We have the impression of a black-white situation here. When k is equal to 0, the system is not observable, and when k is different from 0, the system becomes observable. In reality, of course, we have a gray zone. When k is small but non-zero, it will be observable, the system will be observable, but it will be badly observable. So in order for the system to be observable with a sufficient quality, right, we need a k that is sufficiently large. Well, let us do an exercise and check the controllability of this system. Remember that we only need the state equation involving A and B. The system has one input, so we expect a, well, square controllability matrix. The controllability matrix is composed of B, A, B, and then columns up to a to the power n minus 1b. N is 3 here, so we stop at a squared b. So the way we proceed is that we start with b, then we compute ab. Okay, this is this matrix times this one. We select 1 over here, the minus 3, and then we take the scalar product of the last row with b, and this produces a7. In order to compute a squared b, it's just a times AB, right? This is the most efficient way to work. You don't need to compute A square and then multiply by B. And once you have those vectors, well, you put them into the controllability matrix that you have over here. So we'll proceed as we have done in the course of linear algebra and applications. What we'll do is first switch rows. Here we have already a 0. So this one will be the pivot over here. And what we'll do here, we'll take the entry divided by the pivot. So this is a -3, right? And this will produce a 0 over here, a -2 over here, and a +6 over here, right? So the next pivot is this one over here. We want to create a 0 over here. So we take the entry divided by the pivot, so it's -2. And we end up with 1 -3 7 0 1 -3, and as you can see we'll produce a row of zeros. So the system is not controllable. What you could have done instead of working with elimination is to compute the determinant, okay, of the controllability matrix, and you would see that it is indeed 0, so the system is not controllable. So assume that we are given this system over here and that we have to test controllability. So the first thing to see is that of course the output equation is irrelevant, so we don't need it. We only need A and B. Here B has 2 columns, so the system has 2 inputs. Remember that the controllability matrix is B, AB, and A square B. So in our case this will be a matrix that is in R 3 times 6, right? So we need to see if this matrix has full row rank. So are all the rows independent? Well, sometimes it's good to be a little bit lazy and maybe not compute the whole matrix. So what we'll do is, well, of course, write B. That's easy, no calculations needed. 4 and 5. And then what I'll do is compute the first column of AB, so that's A times the first column of B, right? And if you do these calculations, you have -6, 12, and 46. So of course you could still compute these ones, but since we're a bit lazy, we're not going to do this, right? So this corresponds to B, AB, and A square B. So the question is, can we already see that this matrix has full row rank, even without computing these? Well, you can. So what we'll do is proceed as we have done in the course of linear algebra. We'll switch the 2 rows, so we have 2 -3 12, and of course elements here that we have not computed. We have a 0, -1, -6, an element that have not been computed, and now here we have 0, So I would like to have a 0 over here. I'll use this one as a pivot. I need to produce a 0 below, so it's entry that we want to make 0 divided by pivot, so it's a 2 here. And what we obtain is a 0. We have 11 over here, and we have 22 over here, and elements that we are not going to compute, right? Well, what we could do is produce a 0 here below, right? And what we will see is that since these two vectors here and this one are independent, we are going to produce something different from 0, right? So we can see, even without computing these elements here, that this matrix, see this controllability matrix, has indeed full row rank. The 3 rows are independent, so this system is controllable. What we could do also is work with determinants. So in order to prove that this matrix C has full row rank, we have to find a 3 by 3 matrix that has a determinant that is different from 0. Well, if you compute the determinant of this one over here, 0 minus 1 minus 6, 2 minus 3, 12, 4, 5, and 46, you will see that this determinant is different from 0, which is again a way to see that this system is indeed controllable. Well, suppose now that we are given this state space description of a system and that we have to test if this system is observable. Well, of course, observability depends on outputs and states, so first thing that you have to realize that this information coming from you is irrelevant. We have to consider the unforced system, right? So what we need to do is compute the observability matrix. It's constructed from C, CA, up to C times a to the power n minus 1, n is equal to 3 here, so we stop at C a squared, and we have to see if this matrix has full column rank. This is the question. So this is indeed C. We compute CA. This is what we obtain, and please don't compute a square and then multiply C times a square. No, what you do is to take CA and you pre-multiply a by CA, and this will indeed lead to CA square, right? So what we'll do now is use what we've seen in the course of linear algebra and see if we can see if this matrix has full column rank. So the pivot is a 1 over here, so we'll produce a 0 over here, and the multiplier will be minus 2, and we'll produce a 0 here, this value, and we need to do this operation, and the multiplier will be 4. So we'll obtain, obviously the first row remains the same. We'll have zeros here and here. We'll have minus 5. By the way, this is a 16, I see. Okay, and we'll have a 16 over here. This is because we have a 0 over here, and we'll have minus 2, and we'll have a 7 over here. Okay, so what we can do is continue, but we see that we don't need to continue because these two here are independent. So if we create a 0 over here, the element that we'll have here will be different from 0. So indeed, this matrix has full column rank, and this system is observable. So what we could have done is compute the determinant of the observability matrix, and if you do this, you'll see that it has determinant -3. So indeed the system is observable. In the following slide, we see that controllability and observability are really system properties and not properties that are related, for instance, to a given state space representation. So remember that if we consider the pair AB, we can compute the controllability matrix as follows. Okay, so suppose now that we use a non-singular similarity transformation T, we can go to a new pair of matrices A bar, B bar, which are related to the original AB by T minus 1 AT and T minus 1 B, right? So now we can compute the controllability matrix for this new equivalent pair. And if you look at it, for instance, we can do this for A bar square B, and this would be the third column of this matrix. What we have is T minus 1 AT, T minus 1 AT, and this is A bar, and then B bar is T minus 1 B. Okay, so what will happen is that these ones will cancel out, these ones will cancel out, so we'll have T minus 1 A square B. And we have done this for A square B, but we can do this, for instance, also for A to the power n minus 1 B, right? And we'll have the same thing. So what we'll have is that C bar, the controllability matrix for this equivalent pair, will be T minus 1 times the original controllability matrix. Okay, and since this is a non-singular matrix T, the rank of C is equal to the rank of the controllability matrix for this equivalent pair. So we see that we do not lose controllability if we change the state space description using a similarity transformation. This means that controllability is really a system property, and what we have shown for controllability, of course, can be proven also for observability. Remember that in the previous section we had looked at this single input, single output transfer function b1 as n minus 1 plus b2 as n minus 2 up to bn divided by Sn plus a1 Sn minus 1 plus up to an. Okay, and we had written it as bs polynomial in S over as, and we had seen that we could find a so-called controller canonical form. Well, knowing what we've seen previously, you can now construct the controllability matrix, and if you do the calculations, this is what you obtain. You see here that you have BC, here you have AC, BC, and so on. It is not shown, but it can be shown that this controllability matrix can be constructed from the inverse of this matrix over here. And notice that this controllability matrix is simply constructed from the coefficients of the A polynomial, which is the denominator of h of s. As you can see, this controller canonical form is controllable by construction, because you see here that all rows are independent. Okay, we have a lower triangular matrix, so the determinant of this controller or controllability matrix is simply the product of the elements on the diagonal, so that will be 1. In the next section we'll introduce state feedback, but what will happen if we apply state feedback is that the state matrix in closed loop will become AC minus BC K, where K is some vector K1 up to Kn, right? And BC is given over here. So if you look at this structure here, because we have all zeros except here in the last elements, if you do AC minus BCK, what will happen is that this matrix will have exactly the same structure. The only thing that will change is the last row, but AC minus BCK will still be in controller canonical form. And since only the elements here below the main diagonal will be changed, you can see that the determinant of the associated controllability matrix will still be 1. So the system after state feedback will still be controllable. So we've seen that the determinant of the controllability matrix associated to the controller canonical form is 1, so this form is always controllable. We've seen also that if you use state feedback, you end up with a matrix that looks like this one, and in which the controller canonical form is preserved, in the sense that we only change the last row. So what we would like to do is find the similarity transformation T, right, that will transform any given realization of the system, the one we start with, A, B, C, D, into a system in controller canonical form. We have just seen in the previous slides that the controllability matrices are linked by this equation here, which involves the inverse of the similarity transformation. So T can be isolated and you obtain this equation over here. So you start from any realization. This is something that you can construct, right? It's simply B, AB up to an minus 1b, right? And in order to construct this one here, well, you need the AS polynomial. Remember that h of s is b of s over a of s. So how can you obtain a of s if you know a realization? Well, you know that h of s is simply C Si minus A inverse B plus D, right? So if you have the realization, you can compute h of s and you will have the denominator polynomial. And if you have the denominator polynomial, you can construct this matrix. So you can construct the similarity transformation T that will take me from the given realization to the controller canonical form. So to be clear, T is CAB times the controllability matrix in the controller canonical form A, C, B, C here inverse, okay? And this matrix here, since this one is equal to this one inverse, well, this matrix over here, right, must be this one over here, okay, without the -1, right? Since you have A of S, this matrix is easy to construct, as you can see. So finding this similarity transformation is really easy. If you have a look at the slides, you will see that I have skipped quite a few slides that are there for your information. Slides about duality, the other canonical forms, controllability, observer and observability canonical forms, and the Popov theorem. As we have seen previously, some modes are uncontrollable. If the modes that are not controllable are stable, then we say that the pair AB is stabilizable. Of course, if you have uncontrollable modes, and if these modes are unstable, then you really have a problem, because this means that your system cannot be stabilized using state feedback. We have a similar definition that concerns unobservable modes. Well, if these unobservable modes are stable, we say that the pair AC is detectable. So what we'll do now is look at the case where the system is not controllable. This means that the controllability matrix C has a rank KC that is smaller than n. Remember that n is the number of states. Well, if this is the case, it is possible to find a non-singular T, which is a similarity transformation that transforms the state X in the state X bar. And as you can see, X bar is decomposed in states that are controllable. This is what we mean by the C here, and in states that are not controllable. So C bar means not controllable. And if you look at the representation, the state space representation, in using this new state X bar, this is what you will obtain. And you can see indeed that this state here is not controllable. It is not influenceable by EU because we have a 0 over here, and it cannot be controlled indirectly through X bar C here because we have a 0 over here, right? Well, although the overall system is not controllable, we can say that the pair AC BC bar are controllable. Okay, so this is the uncontrollable part, and this is the state matrix that is related to this uncontrollable part. If this part is stable and that these eigenvalues of this matrix have all a real part that is negative, then we say that the system is stabilizable. The uncontrollable part is stable. We can now have a look at what happens when the system is not observable. This means that the observability matrix O will have a rank that is smaller than n, right? Well, again, there will be a non-singular similarity transformation that will transform the original state X in a state X bar. And using this state X bar, we have this decomposition in, well, states that are observable. There will be exactly KO states that are observable and states that are not observable. If you have a look at the state space representation, you will obtain a matrix A that is decomposed as follows. Okay, and you can clearly see that this state over here is not observable because we have a 0 over here, so there is no direct link between this part here, this unobservable state, and the output, but it cannot also not be observed indirectly because we have a 0 here. Okay, we see that this part of the state is not influenced by this part of the state. So clearly this part of the state is unobservable. Although the overall system is not observable in the sense that AC is not observable, this pair A0 bar C0 bar is observable. If the matrix, okay, the state matrix that is related to the inobservable part is stable, okay, and this is this matrix, this means that it has eigenvalues with real parts that are negative, we say that the system is detectable. Its inobservable part is stable. We can now combine what you've seen in the two previous slides. Suppose that the controllability matrix has a rank Kc smaller than n, the number of states, and that the observability matrix has a rank K0 smaller than n. Well, then it's possible to find a non-singular similarity transformation T that will take the state from X to X bar, and you'll end up with a state space description that looks like this. So this type of similarity transformation exists, and what it will do is decompose the state X bar in such a way that you have states that are controllable and observable, states that are controllable but not observable, states that are not controllable but observable, and states which are not controllable and not observable. You can see here that indeed these two states are not controllable because they cannot be influenced directly through you. This is because of the zeros over here, and you can see because of the presence of the zeros over here that they cannot be influenced indirectly using the states that are controllable because of the presence of the zeros over here. Similarly, the states here in blue are observable and the one in red here are unobservable, and this is because we have the presence of zeros over here, so that the states in red are not directly influencing Y, but because of the zeros over here there is no influence of the states in red on the involution of the states that are observable. Okay, so this is why we see here that the states in red are unobservable. Well, we can also see that the realization that we've got over here, right, the overall realization A, B, C and D is called a non-minimal realization. You can construct a minimal realization using, well, the matrices that are related to states that are controllable and observable. And such a realization is called a minimal realization. Minimal in the sense that the minimal amount of states is used. If you compute the transfer matrix of the system, right, even if you use the original realization A, B, C, D, so that you use C, Si minus A inverse B plus D. What you'll end up with is with this transfer matrix computed from this minimal realization. So you see that in the transfer matrix you only retain the information about the states that are controllable and observable. Everything that is unobservable and or uncontrollable disappears from the transfer matrix. This is why we call this an external description of the system, in the sense that you're only interested in inputs and outputs. This is also called an input-output description, right? Everything that has to do what happens internally disappears from the description. So before designing a state feedback controller, you should check controllability, and before designing an observer, being it a reduced order observer or a full order observer, you need to test observability. So for controllability, there is this command ctrb, which computes the controllability in Matlab, and there is something similar for the observability matrix. Okay, and in order to see or to compute the number of uncontrollable modes, you do the length of A. A is a square matrix, so length of A is computing the number of rows or columns minus the rank of this controllability matrix, right? And in this way you can, if this number of uncontrollable modes is 0, then you know that your system is controllable. Similarly, you can do something here to compute the number of unobservable modes, and if this number of unobservable modes is 0, then you know that your system is observable.